will get here in one. But document two, because it does not include the word Alice, will not get here in one, will get something else. And the second word is Dorothy, which does appear in document two, so it gets two here. Now, I guess I'll break here for a short for a break, but I want you to think that what are we gonna get here? The more similar these documents are, the more likely it is that they will get the same value, document one and get document two, because for it to have the word for this to get the same value, a word among the intersection has to come before a word outside. So okay. And any questions so far? All right. Let me take a short break. We'll continue in like 20 minutes or so, and we'll finish up with this. Okay. Okay. So I'm gonna take a break. We'll start again. Okay, guys. Let's let's continue here. Right. So let's continue here. So where we were before. Do I have any questions about it? Did you think about it? Yeah. Again, if you have any questions, you have to just speak up. Uh, so let's see. So where are we now? We said earlier that what we want is we want to find similarities between documents where the documents are basically mapped to vectors. They're sets of words that that we use the vector representation. So a document is a set of words from a universe, like all the words in a dictionary, and we want to identify to compute the similarity using the Jaccard coefficient. Jaccard coefficient is just the intersection of two sets, the size of the intersection over the size of the union of the two sets. Um, Now, again, as we said, if I only have two documents, this is relatively trivial to do. I just take this vector here and this vector here. I can compute the intersection. The intersection is just how many places they both have ones. So it's the end of the two bit vectors. The union is just when either one has an one, like here, 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 here. So it is the OR of the two bit vectors. And then I can compute the ones in the end of the two vectors, and then that's the size of the intersection, the number of the ones in the or of the two vectors, that's the size of the union, and I divide. That's the that's the intersection, that's the Jaccard coefficient of two documents. So it's trivial to do if I only have two documents. Uh, but if I have more than two documents, if I have many documents, this kind of technique does not give me a way to kind of index or do some kind of some kind of processing that will allow me to find the nearest, the most similar document faster than the brute force way of checking of computing the Jaccard coefficient of the document versus every other document. So we're looking now for alternative ways that will allow us to compute to find the more similar documents faster than computing all the similarities. As you remember, this is the whole, I mean, this is what we've been doing in this class from the beginning, right? I mean, we always said that, the nearest neighbor can be easily computed by just taking the distance of an object to everything else. But the goal is doing it faster than that, and it's not always possible. So in our case, so we said, okay, this is so we have to develop some kind of machinery that both can compute the similarity between the the uh, the two sets, and also be able we should be able to do it faster uh, than just looking at brute force way. Uh, so the way to do it, you get some idea of how to proceed in this kind of problem when we did dimensionality reduction. And what did we do there? We had a distance function in the original space, and the original space was a space with a lot of dimensions. Uh, and the problem there was that in a lot of dimensions, it was difficult to come up with an index structure, the index method, an index mechanism that will allow us to zoom in and find, the most similar objects quickly. So what did we do? I mean, we did a transformation. We took the original space and transformed it to a lower dimensional space with the hope that in the lower dimensional space, the index methods that we knew that work in lower dimensional space could be applied and therefore, be used there. So something like this, we're going to do it here, but here it's an additional complication because our original space is not just a high dimensional space. I mean, it is a high dimensional space because originally we have documents which we see, we view them, we represent them as vectors, as bit vectors of very large length. I mean, the length of the vector is equal to the dictionary size, all the words. So it is a very high dimensional space, but that's not it. That's not the only problem. The other problem is that the way we compute the similarity or the distance, we don't take something like a Euclidean distance. We don't take something like even L1 or something like this. We actually use this kind of different beast. I mean, it's a different thing. The Jacquard coefficient, which is the intersection over the union. And there is no easy way to take something like the Jacquard coefficient and map it to kind of a lower dimensional space Euclidean distance. And yet, that's how we're going to proceed. I mean, what we're going to do is we're going to take something like uh, the the Jacquard coefficient, and this with the Jacquard coefficient of sets which have potentially very large size because they are taken from a universe which is in the tens or hundreds of thousands size, and transform it to transform this Jacquard coefficient to a distance in a much lower dimensional space, distance between vectors in a much lower dimensional space. And the instrument, the way we're going to do it is this function here. It's called mean-wise independent permutation, and it is what I described earlier. So how does it work again? So I'll just very quickly recap how it works. I will say that, we have a list of words. These are the elements of the universe. These are words in our example. And I shuffle them. I take a permutation, a random permutation of these words. And this random permutation is defined by these arrows here, which tell you that, Trish is the first word after the shuffling, cowardly is the second, and so on. And then what I do, these are all the words, right? And then I look at, for each document, which is the first word of this document that appears in this order. The order is Trish, and then Cowardly, and then Alice, and then Dorothy, and then Party, and then Tears, and then Tea Party. And it turns out, that the first word is Trish, because Trish appears in this document. And it's the same for the second document. Trish appears in the second document. And then I do it a bunch of times, same thing, changing the random permutation. Take a different random permutation, That's what we said before. And here I take another random permutation that I said before. And then notice what is happening here. What is happening here is the following. If in this order, the first word is one of these, then both documents have here N1. If in this order, the first word is not one of these, but it's one of Alice, T, Cowardly, or Dorothy, then they are going to have a different number here. And therefore, what is the probability that they will have the same number here? Because this is a random permutation, the probability that they will have the same number here is exactly the probability of getting one of these words out of this many. Because I pick words here at random to be first, and you know, if what is the probability that one of them will be the first? Everyone is 1 out of 6. So a word here has 2 out of 6 or 1 out of 3 chances to be the first. And if one of these is the first, then they will get the same number here. If one of these is the first, they will get a different number here. So in other words, for each one of these, the probability that they are the same is exactly equal to the Jacquard coefficient of document 1 and document 2. Now, this is not difficult to see, but this tells you something. It tells you that by taking a number of random permutations, and each one has probability 1/3 to be the same, after I do d of them, let's say 10 of them, and if in 10 of them, 3 are the same, then I can be fairly sure that the Jacquard coefficient of these two is 30%. It's 3/10. And if 9 of 10 are the same, then I can be fairly sure that the distance between the Jacquard coefficient, no, not the distance, the Jacquard coefficient, because between document 1 and document 2 is 90%, 0.9. So these two vectors here, and in fact, not these two vectors, but how often these two vectors agree, this is an estimate on the fraction of these locations that agree is an estimate of the Jacquard coefficient between these two documents. Okay. Any questions so far? Any questions so far? Okay. So for example, let's just to continue the example, if I run this 4 times, and the example that I gave you, I already had the 3, and then I did the 4. The 4th, this is my my 4th random permutation. Tears would be the first word, and Cowardly the second, and Tris would be the third, Alice would be the fourth, Tea Party would be the fifth, and Dorothy would be the sixth. So in this random permutation, the first word is tears. The tears is here. So both documents would get 1 and 1. After 4 random permutations, the first document has this kind of a vector, 1, 2, 1, 1. This document has this kind of a vector, 1, 1, 2, 1. And the places where they agree are 2. So they agree in 2 out of the 4, 1 out of 2, 0.5. So the estimate that we have for the similarity, the Jacquard coefficient of document 1 and document 2 is 1/2. 0.5. We know that the actual value is 1/3. I just look here, and this is 2 out of 6, so the actual value, 2 over 6, so the actual value is 1/3. The estimate that we got just doing 4 trials, each one half. Of course, with 4 trials, I mean, we don't get a lot of resolution, right? I mean, they can only agree in 0. If they agreed in 0, then we would estimate 0, or they would agree in 1 out of 4, then our estimate would be 0.25, or they would agree in 2 out of 4, like in this case. So the estimate of our similarity is 1/2, or they would agree in 3 out of 4, so the estimate would be 3/4, or they would agree in all 4, so the estimate would be 1. So the only 4 trials don't really give you a lot of resolution, not a lot of confidence either. I mean, just random trials, right? But the more trials you make, so the larger this D is, the closer this estimate is to the actual value of the Descartes coefficient. So what have we achieved? So what we have achieved is that instead of having sets and query sets, we now have vectors. So instead of having these long sets here, we just have this kind of vectors for each document. And these vectors, I mean, these original documents could be hundreds of thousands long, right? I mean, it could be a long document, could be a small document, but potentially it could be, very large. Um, but these vectors, they are not so large. I mean, it depends on how good your estimate you want it to be. But for example, you probably never have to have a D as large as 100 even. Like some smaller number would get you good estimate if you want, to compute the similarity with a reasonable number. I mean, if you want to say something like, I want the similarity to know if something is at least 90% similar, then probably you need something like 10, 20 trials, not even more than that. If you wanted to have, of course, documents that are at least, for example, 93.5% similar, then of course you need a lot of more dimensions. But this 93.5, I mean, it's quite unlikely that you will get such a requirement. You probably get the requirement something like, give me something which is 95% similar or 90% similar, something like this. And for that, your D doesn't have to be very large. So immediately you translate, you did the mapping here from a very high dimensional space, the original document, to a space which is much more manageable. It's like at the worst, something like 50 dimensions, something like this. But it's orders of magnitude less than your original space. So just there, you actually win. And instead of doing computations in the 100,000 dimensional space, you do computations in a 100-dimensional space. So it's 1,000 times faster, and the actual space that you need for the document to compute the similarity, it's 100 times less, or something like this. 1,000 times less. It's many orders of magnitude less. So this by itself is useful. Of course, you paid for something, right? I mean, you have an estimate here. You don't have the exact value. And to get a better estimate, you need to pay for it by getting this D to become larger. So the larger the D, the better your estimate. But at some point you say, okay, I don't really, I'm really not interested in knowing, if this similarity is 92.5 versus 95. This is, both of them are going to be high similarity. And if I want, this is what people do, if I want to have the exact similarity of my most near, then after I get an estimate, then I can go and compute the exact one. But now I only have to compute the exact one for the ones that have a very high estimate, not for everything. So what we have achieved is this, that we have, instead of a high dimensional original space of sets and so on, we actually have vectors uh, that are much lower dimension, and we want now to find vectors which have the same coordinates, have a lot of similar coordinates with the query vector. The problem here is the following. Okay, so we have these vectors. These are, I got four numbers. This number is 7, 10, 5, 3, and 7, 10, 13, 1. So this means that, these two have a similarity of 1/2 because they agree in the first. I'm sorry. Agree in the first two. So it would be nice to somehow, be able to look at these two vectors and say, okay, the similarity is half. So one thing that people can thought about is, say, okay, let's take this one and write it as a binary vector. This is the binary vector. This is a binary vector. This is another binary vector. Let's look at the similarity of these two binary vectors. It's not exactly the same, right? Because I care, if 5 and 30 are the same or not the same. And 5 and 13, the binary representations are quite similar. This is 0, 1, 0, 1, and this is 1, 1, 0, 1. So 5 and 13 actually quite similar if you represent them as binary, but they're not the same. And I care only if these two are the same or not. So it's not really doing the it's not really taking these two binary vectors and looking at the binary vectors that are most similar. Okay, so there are some ways to address this, but really in the work that we will do, the work that you will see, okay, we'll sort of sweep it under the table and say, okay, really, I'm going to look at the similarities between uh, these two binary vectors. So I will take the two I will basically think about them having two long binary vectors, not two, one long binary vector per set, and I'm going to store these binary vectors of each one of the sets in such a way that when a new set comes in, which have a new binary vector signature like this, I'm going to find quickly which other binary vectors are very similar to myself. And this will give me a first cut. It will give me a first idea on which documents are likely to be very similar to me. And also it will give me another thing. It will tell me which documents are very unlikely to be similar to me. And therefore, I can I can throw them away and not check them. So now for the remaining of the class, I'm gonna give you the intuition of how this works. Uh, the basic idea, uh, okay, let me go back here. The basic idea is the following. Uh, the, 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 the thing that will, so again, I mean, what do we want? I mean, we're going to have several sets, and for each one of the sets, we're going to have, each one of the sets will be represented by a signature, a long signature like this. It's a 0, 1 value, right? So it's a binary representation of the set. How big this is? Um, it depends on how many trials I made to create to create these vectors. Each of these vectors has a value. This value came from an independent, meanwise independent permutation. So depending on how many permutations that I took, I fix this, the number of permutations fixes this D, the number of permutations. It creates this kind of, uh, D numbers one after the other, and then I take the binary representation. So this here is just D times the number of bits that you write every integer, depending on how do you do the transformation from the denary decimal, the denary number to the binary number. But you know, if I have D here, I may have something like if these are D numbers and everyone is an integer, maybe 16 bits per integer. So this is like 16 times D bits. So if D is like 10, it's a reasonable number. If you want an accuracy of like 10%, so this is going to be 160 bits. So this is going to be 160 bits, and every document is going to have this 160-bit representation. And okay, so I have this 160 bits here, and I want to find several documents which have 160 bits here, and I want to store them in such a way that when I come up with a new query, which is another 160-bit representation, I will basically, I will be able to compute, to find those 160-bit representations that are very similar to the query. Now, we are going to use a mechanism which is called locally sensitive hashing. And what is the basic idea of localization? So as you know, hashing is a technique that can tell you quickly if something appears in a set, right? I mean, it can solve inclusion-exclusion queries very quickly. Either you have something or you don't, and if you have it, hashing can get it very quickly. So hashing as a technique looks for things that are equal. You cannot really use hashing to find similar things. But locally sensitive hashing is an extension of hashing which can be used to find things that are similar under the provision that are very similar. So if I have two bits like this, if I have a, sorry, if I have 160 bits like this, and I want to find uh, other documents that are very similar to this bit representation. And by very similar, I mean 90% similar. 90% similar means that there are at most 10% mistakes, 10% changes. So out of 160, there can only be 16 different locations. Everything else has to appear the same, right? Everything else has to appear, look the same, and only maybe 16 locations that can be different. So the idea of locally sensitive hashing is that, if I want to find things that are so much similar, then this means that there have to be parts, smaller parts, maybe this part, maybe this part, maybe this part. They have to be smaller parts in the query that are exactly the same as the same parts of the document that is very similar. So I can exploit that because, of course, this would not work if I wanted things that are like 50% similar, because 50% similar would mean one out of two would be the same and the other would be different. And this means, the first is the same, the second different, the first the same, the second different. So there is no place where, there's no guarantee that there is no place where there is a bunch of uh, of objects of locations that are exactly the same as the query. So in our case, though, we want to have locations. So yeah. So you need, as I said, you need to look at in this case, in our case, if we want to find things that are very similar, there have to be some places that are exactly the same. And getting things that are exactly the same is exactly what hashing is good for. So instead of actually taking this entire query and this entire signatures for each one of the documents and put them, for example, in a hash table, what we do is we break them into pieces, smaller pieces. We pull them into bands. Let's say, I had 160. I can partition them in 10 bands. The first 10, the second 10, the third 10, the fourth 10, the fifth 10, 16 10. And each one of these bands are stored separately. So this is what happens here. I partition them into pieces and I create a different hash table for each one of these pieces. So in this hash table, I take the first piece, the first 10 bytes, the first 10 bits, and here I put the second 10 bits, and here I put the third, and so on, and here I put the last 10 bits. So how does it work? I mean, the idea is the following. When I come up with a query, I will partition the query also in these 10 bits, 10-bit pieces. And I will take these 10 bits, the first 10 bit, and I will search in this hash table. And I will find if there is at least a document which has the same first bit, first part, or a document that has the same second part from here, and so on. And the thing is, if there is a document that is very similar to the query, it's going to show up somewhere here, in one of these things as the part being equal. That's basically how this technique works. It basically partition this into pieces, and using a separate hash table for each one of these pieces. And when a new query comes in, I will again do the same thing, a partition, and I look to find a document which is exactly the same with the query in at least one of the pieces. And if it is the same as one of the pieces, then I use it as evidence that these two documents can be very similar, and I compute the actual similarity. And it turns out that this worked quite well. Any questions so far? This is not an easy concept, you know, how this how this function, how this indexing method works. Anybody has a question? No questions so far. Okay. So I'm gonna skip this. I'm gonna skip this because I really just want you to focus on how this works. Any other questions? So look at what can happen, right? I mean, what can happen? One thing that can happen is the following. Two things. So I take this, the first, um, part, and then I look at this hash table and I find all those documents that have the same first part. It is not clear that all of them are actually very similar to the query. So we're going to have what is called a false positive. So somebody will tell you, okay, this is very similar. One of the documents is very similar, but it just happened. You were unlucky, and it's very similar all in the beginning, and the rest of it is not similar. So this is not a good example. So you will get some documents like this. And also, it might be the case that, okay, you partition it into 10, and for some very unlucky reason, you had exactly, you partitioned it into 16 groups, each one of size 10, and for a very unlucky reason, your most similar or very similar document, 90% similar document, had exactly 16 errors, one error in each one of and you never found this document because each one of 10 documents has one difference. Each one of 10, each one of the blocks of size 10, they have exactly one difference. And that's also very unlikely because it happened exactly, I mean, to have one mistake every 10, exactly like this, the one, but it could happen. So that's a false negative. So you thought that this is not similar to the query, but actually it was similar to the query. So you are going to have some false positives and some false negatives for sure. And the question is how you are going to how you're gonna control, the size of false positives and false negatives. And we'll see next time, because I'd like to have the blackboard to show that. We'll see next time that you can control, the number of false positives and false negatives by using a number of things. One of the things you can use is the size of this query, the size of this representation, which means how many trials you make. You can take into account what is your threshold similarity. Do you care about 95%, 90%, 80%? And also you can look at, uh, how many, how big this these blocks are. You know, the more of these blocks, the more the hash tables. The fewer of these blocks, the larger they are, the fewer hash tables. So these are the things that you can play with, and by using the right combination of values, you can actually try to minimize the number of positives, false positives, and the false negatives. Okay. So for today, I will stop here because I have a little more to talk about it. We'll talk about it next time. But this gave you an intuition and or not intuition, actually how it works. So next time we'll just prove this kind of bound here, and then we'll go on. Okay. Any questions so far? Yeah. All right. So I don't have any questions. So I'm gonna stop here for today. Yeah, sorry, apologies for today. Uh, Hopefully next time will be from the classroom. I'll stop recording, and I'll put this recording also the one I have, the one from the previous time that we had to do the WebEx. I will add that recording as well to the class. Okay, so this is up. This is it for me from me for today, and I'll see you next time. Okay.
Γεια σας και περαστικά.
Γεια χαρά.
Γεια.
Συγγνώμη, μια επισήμανση.
Ναι.
Μπορείτε μήπως να δείτε λίγο τα αιτήματα στο e-class, γιατί είμαστε μερικά άτομα που σας έχουμε κάνει αίτημα και δεν μας έχετε βάλει.
Τα είχα κάνει όλα στην αρχή. Αργήσατε δηλαδή να το κάνετε. Οκ, θα τα ξανακάνουμε τώρα.
Μας φτιάξανε μετά τους λογαριασμούς σε κάποια άτομα.
Θα το κάνουμε.
Ευχαριστώ.
Ναι, γεια σας.